Yes, it is. So it asks quite specifically for you to say when what the maximum power delivered to the dog sled is. So all of you who are no longer paying attention, this is where you pay attention. Because I want you to think about this for a moment, just a moment. We have the sled, whatever's all on here, and then the dogs are pulling it, and there's some friction pulling backwards. Not a whole lot, but there's some. Now, this is an unbalanced force. So the net force equals ma. The system is accelerating, and they tell us what the acceleration of the system is. Now, you have to understand that they want the acceleration to remain a constant. So you're always getting faster. It's not that you're moving fast, it's that you're always getting faster than you were a moment ago. I want you to imagine you trying to run like that. They're talking about the dogs. This is an impossible circumstance for any length of time because you're going to reach your maximum speed eventually, to which you can't go any faster. But they're saying that the dogs are applying a constant force, and therefore the system is constantly accelerating. So if you have to pull something and you have to accelerate it the whole time, you realize that you're going to have to be working harder and harder and harder and harder, because every moment you're going faster than the moment before, and you're still pulling something. So now you have to go even faster than before. That's why power, when you're trying to apply a constant force, gets greater the faster you go. So when you first pull on the sled, it's not moving anywhere. No work's being done in that instant. Therefore, there's no power delivery. But in the next instant, when you begin moving, because you have accelerated the cart now, you have a little bit of power. And the faster you go, the more power you deliver. So you don't reach your maximum power until you reach your maximum velocity, which that's at 15 kilometers an hour, which you will have to convert to meters per second. Now, herein lies the other thing. They didn't ask what the net power delivered was. That would be the power from the net force. They asked what the power delivered by the dogs was. Well, there's the force from the dogs minus the force from friction, and that had to equal ma. So this F represents the force from the dogs, because they have to overcome friction too. This is the maximum power delivered by the dogs to the sled. So you need to have and this will be the max power. All right, that's it. That's number 11. I mean, there's a part B in there. So what is the team's power output during the cruising phase? Well, are we accelerating any longer? We're no longer accelerating, which means suddenly the net force equals 0, which means the dogs are pulling at a force equal to the force of friction. So the only difference now is that the power you're applying will be the frictional force times 15 times 1,000 over 3,600, or UMG. Good enough for you guys? It's good enough for high school. I know. That's why your test's really hard in this. But it's an okay power question. It's not great. But power is a footnote. It's in real life, power is not a footnote. But for the AP exam, they really don't make it a big deal. It's less than 2% of the questions, so it's pretty small. All right. Yay, I can do physics. Next. Doesn't matter if I can do physics. You have to be able to do physics. So Sana has her hand up. We already heard from somebody at home. How about a person in here? Yes, Alex, what do you got? Number 14. Number 14. Is this a stupid one with the force going up the ramp? All right. So how hard do you want me to make this for you guys? There's a lot of ways that you could do this question. And they have asked for you to do it a specific way. So because of that, we're going to do the way they have suggested. But I want you to know that you could easily do this problem a different way and still get the answer. They've asked specifically for you to do this using work. So for us to follow what they've said, we're going to use the definition of work. But I could think of probably 3 different ways you could do this question. Come on, stop being a jerk. There we go. Oh, that's so hard. There, it's not even. Come on. All right. Woo. There we go. Oh, that's so small and wee. There we go. So there's 2 things about this problem that make it weird. First, they want it all in terms of the height. And in addition to that, they apply the force horizontally. So you could find the net force, set it equal to ma, and use that to figure out the acceleration when the box makes it to the top. Motion equation. You could do it that way. They asked specifically for you not to do it that way, but you could. You could treat this as a conservation of energy problem and do it that way as well. But they want you to do net work. So we're going to do net work. Now, I want you to see this. This is a teachable moment. So I'm going to try and convey something to you that might not be obvious. So are you ready? I can think that at least at the onset of this question, the box is going to be pushed up the ramp a distance L. I know I'll have to convert that to H later, but for right now, the box's displacement is from the bottom of the ramp to the top of the ramp. And that's a distance L up the ramp. These are all non-conservative forces. There's no friction involved. Because there's no friction involved, these forces all act path independent. You might not understand what that means right now, but it's going to become an important distinction as the year progresses, that because we don't have a frictional force acting in the system, the path length actually doesn't matter. But I'm still going to treat this problem from the standpoint of the reality of the question, and that is it is traveling the length of the ramp. So because of that, I know that there's going to be work done by F, the applied force. Let's deal with that work first. And that work is pretty easy because F is a constant and the box is going to travel up the ramp, which presents an angle of theta between up the ramp and F. So my total work done is going to be F times L times the cosine of theta. That's the work done by the horizontal force for the box to travel up the ramp. I know I have to replace L later. Now, there's the work done by gravity. I can apply this principle 2 different ways. I could look at mg and the angle between mg and the displacement. Or I could look at the component of mg down the ramp and the component of mg into the ramp and look at them separately for this. Which way would you like to do it? This way right now? Okay, so if I do it this way, it's just going to be mg times L times the cosine of 90 plus theta. Do you understand why it's 90 plus theta? We have talked about it, but I want to make sure. Okay, there is another force doing work on this system. Or let me say that different. There's another force acting on the system. There's a normal force acting on the system. does the normal force do work on the system? Now, I'm bringing up the force from the normal force because I have an important reason to do so. We could choose to do this problem differently. And because of that, there is a way you can do this problem where the normal force does work and the horizontal force doesn't. We could look at the path independent version of this problem, where we consider the box just going straight up and not going to the side. Just look at the y portions of everything. Under that circumstance, we would change the nature of how we evaluate this. We can do it because they're all conservative forces. But we've chosen to go up the ramp this way, which means normal times length times the cosine of 90 degrees. This is the work done by each force that acts on the box, but one of them is 0. Right, Jaden? Right. So when I add these 3 forces up, they're going to equal the change in kinetic energy of the box. So let's do that. FL cos theta plus, just so you guys know, cosine of 90 plus theta. How many of you know how to deal with this? How do I deal with it? Nope, but you're close. Minus sine of theta. It's a good one to know. And if you don't know why that's true, I can show you. Would you like me to show you? I think you should just know things, but I understand why you sometimes don't. There's a lot of things to know in life. I don't know why I know this, but I do. That's theta. So 90 plus theta is over here. Okay? So if we were looking at the cosine, we were looking at this distance, right? The cosine of theta. But if we want the cosine of 90 plus theta, that's this distance, clearly the sine portion right here. But it's negative. So that's why cosine of 90 plus theta is negative sine theta. Okay? Where's my work? There it is. So with that being said, this is going to be plus mgl times minus sine theta. Now, don't take this too hard. Do you notice that what this really is just mg sine theta times L with a negative sign? It's what would have happened if we had said that there's mg sine theta going down the ramp, but the box is going up the ramp. That's why we get mg sine theta times L with a negative in front of it. It has to work out this way. Has to. So, anyways, long story made even longer. This still has to equal the change in kinetic energy. So now our last thing to do is to get rid of L, because we can't have this in terms of L. And when I look at this, I see, cosine, no, not cosine. Sine of theta is H over L. So L equals H divided by sine of theta, except my head's in the way, so you can't see that. Probably. Is my head in the way? There. I should just make myself disappear anyways. So any place I see an L, I got to put an H sine theta. So F times H over sine theta times cosine theta plus mg H over sine theta times negative sine theta equals change in kinetic energy. Almost there. So all that's left now is for us to kind of finish this off. I get FH cotangent theta minus mgh equals 1/2 mv squared. That's the end. And yeah, I haven't solved for V. But you guys, this shouldn't be a surprise. Move it over and just think about what this is. The box started here. We gave the box energy. How much energy did we give it? We gave it this much energy, which is actually FL cosine theta. That's how much energy we gave the box. When we were done, the box is up here, so it has potential energy. But there was more energy given to the box than just what it has in potential energy, which is why it's moving. That's it. Conservation of energy. I gave it this amount of energy. It has it split between gravitational potential and kinetic. Has to work out this way. All right. Well, that was a lot of fun for me, really. I enjoyed that thoroughly. Is that good for you, Alex?
Yeah.
Excellent. Okay, who's next? See, Ryan's got his hand up. And was there anybody at home who had their hand up? Nope. Oh, Alex at home has his hand up too. All right, so let's, Alex at home, which one do you want to see?
Number 12.
Number 12. And Ryan in school, which one do you want to see? So number 12. Yay. So what's your specific question about number 12? Oh, I don't know. Let's see. This is number 12, you said. This is the lawnmower question? All right, let's see, because I haven't done this problem yet. Number 12. So we got a lawnmower and the guy is pressing down on it. Well, the lawnmower has wheels, not blocks. Yeah. Prehistoric lawnmower. We had to use blocks for wheels. Hadn't invented a wheel yet. Oops, that's not right. $37 degrees or some garbage like that. All right, so I don't really know what the problem asks, but I think I know most of the pieces. I don't care about the numbers. They want the power what? How much power does the gardener have to supply to push the lawnmower at a constant speed? So we're talking about the power supplied by the gardener to push the mower at a constant speed. We don't know how much force the gardener uses to push the lawnmower at a constant speed. That's what we need to find out in order to answer this question. So to get the answer to the question, we need, this is the force from the applied to the lawnmower. That's what the gardener applies to the lawnmower. So I don't think there's any way to get into this problem except to go, there are several forces acting on the lawnmower. There's the force you apply. There's the weight of the lawnmower. There's friction, and there's a normal force. I can't see any way around doing this. Can you? All right, so I'm going to cut some corners. Normal equals F sine 37 plus mg, and F cosine 37 equals friction. We good? Trying to figure out F, so we need to figure out what the frictional force is. Friction is mu times the normal force. This is not static friction. It's kinetic friction. So this is going to be mu times F sine 37 plus mg. So it looks to me like I'm going to have F cosine 37 minus mu F sine 37 equals mu mg. Yes?
I don't remember if it was in this problem or not, but when it says like rolling friction, does that mean static friction or kinetic friction?
Rolling friction is a fancy way of saying it's the kinetic friction of the bearings inside the axle of the wheel. So I've just taken to the idea that when you're rolling something, it's static friction between the wheels and the ground, but there is still a certain amount of resistance to that motion because there's somewhere in the scope of all this is one surface scraping against another somewhere. In this case, it's whatever you're using for an axle. So how many of you guys ever mowed a lawn before? Using a lawnmower that you actually have to push. So now, if you don't have a powered lawnmower, like I don't have a powered lawnmower, there's no bearings in the wheels on my lawnmower. It's just a plastic wheel shoved into the side of the lawnmower. So what friction are we talking about? We're talking about the small amount of friction that exists between the surface of the little pole the wheel sits on and the bracket on the lawnmower. Now, the reason there's less friction there is not because of anything fancy. It's just that there's a lot less contact there and a lot less normal force because it's spread out over 4 wheels. But generally, they treat the whole system as if there's one unified coefficient, as if it's acting like kinetic friction. So you just treat it like kinetic friction. So I never brought it up in class because it's not every book describes it that way, and I forgot that this one does. All right, so I think I'm pretty close to the end here. I need to factor out the F and get an expression for the force, which is going to be mu mg over cos 37 minus mu sine 37. Now, this isn't the answer, but if I multiply all this times how fast the lawnmower is going, that's got to be the power delivered to the lawnmower by the person. Yo.
So that's not the correct answer. I know that because I tried exactly that like 5 times on Alex's and mine and Jeff's. So, but how I got the right answer was by multiplying the force times cosine 37 again, and then the velocity.
Yeah, I had the same thing.
Yeah, my face too. Yeah, you know my face.
I think that force is the force that he is originally applying, and you can multiply that with the angle, so we're getting like the parallel force to the motion.
I disagree. No, what I'm saying is, I think if we were to rate the amount of energy lost by the person to push the lawnmower, this is how much energy was lost by the person. I think that they're conceptualizing the answer wrong based on the way they asked the question. Now, I'm not saying that I don't make mistakes. I do. But I think that there's a certain amount of ambiguity here. I'm sorry, I'm not suffering from any ambiguity. If we were to measure the amount of energy lost by the person, the rate at which they lost energy would be based on the force they applied. Them applying a force in this angle created more friction that they then had to overcome with the force they applied. So the amount of energy they lost would have to be equal to this force times the velocity for every second they were pushing the lawnmower. Now, there might be something here where the way they asked the question is suggesting I'm only going to be using the part of that force that's in the direction of motion of the lawnmower to be specific about the lawnmower, but they didn't ask what the power was of the lawnmower or the force applied to the lawnmower. They asked about the amount of power the gardener applied, which has to be the force they applied. So although I think this is ambiguous, I think it's a wording issue. I do not think that would affect your ability to do your exam, because I think it'll be more straightforward than this. But understand that I perceive this as the way the problem should have been done, based on the way the wording is in the problem. I think if they wanted something about that force as it acts on the lawnmower to move it, then they should have said that, and they didn't. So if you did this, I think you did it right based on the wording in the problem. Now, guys, how many times have I taken issue with a problem in the book being wrong? Once? This is it, right? I've said that sometimes I think problems are badly written in the book, but I don't take lightly saying that the answer in the book is incorrect. In this case, I believe the answer in the book does not represent what they're asking us to do. Does that make sense? So I think if you did it this way, I think you did it as you were trained by me, and I think this is correct. But again, I don't take that lightly. So I will do a little bit of research myself, because I hate when I give people false information. But I think this is what they're asking us to do. What number do you get when you work this out? I'm just curious. Because they have some information for us with that I can usually look at to see if they have an issue with it. I'm looking at the teacher notes here, and they say the answer should be 30 watts because they do multiply by the cosine of whatever the angle is. So if you don't multiply the cosine, your answer is going to be greater. Not by much, a couple of watts probably.
The correct answer on mine was 40, and I kept getting 60.
Yeah, when I used that, I got 43 and the correct answer was 35.
Okay. So just so you know, that shows me all the responses that you guys have submitted that were marked wrong. And it looks to me like almost all of them should have been marked correct by the way we just did the problem.
Yeah, I got a 0.
Well, no, you didn't. I just granted everybody full credit. But I want to find out why. Why are they scaling it by the horizontal component? I get why. Don't get me wrong. I get why you would calculate the amount of work done on the lawnmower, but they didn't ask about that. That's why I'm concerned. Yeah. I don't disagree with that. I think if they said, and if they had said the usable work done by the gardener, I'd be understanding my own mistake then. But that's not what they said. And I want to get it right. You know what I mean? I want to understand the difference. Like I said, at the end of the day, if my fitness watch were to show how much energy I lost due to mowing the lawn, I believe it would show that I lost this amount of energy because that's what I expended. Obviously, I should lower the angle of the handle so I don't push down on it so much to create so much friction. That's what I should do. I don't because I'm taller and I don't want to walk all hunched over. But there it is. Oh, interesting. I think if you followed this conversation we're having right now, then I think that you have a better understanding of what's happening in physics. If you didn't follow this conversation, you just want to know what the answer is, well, good luck on the test on Friday. Okay. Is there another question in the homework to which you'd like me to talk about badly? Yes, sir. 15. And by the way, I don't know if the bells are ringing. I don't know what time they are going to ring. So, okay. $700 kilogram elevator accelerates upwards 1.8 meters per second squared for 13 meters, starting from rest. How much work does gravity do on the elevator? Okay. Is there a parts B to this? How much work does the tension do in the elevator? What is the elevator's kinetic energy? All right. All right. Oh, I don't want to narrow.
Like ridiculously easy because I'm pretty sure I got a 0 on it. Maybe I'm thinking the wrong one.
I don't know if it's ridiculously easy or not.
Is it easy? Okay, then don't bother.
That's exactly what I was thinking in my head. So just want you to know, I thought the same thing. Well, I'm going to. I got to let you know. So, okay, there was a joking class. It was kind of funny, but Alex says, is this one ridiculously easy? Because if it is, I don't need to see it. Maybe I just made a mistake, or I'm asking for the wrong question. And then in my head, I thought something, but before I could say it, it was said for me out, and I think it was Max who said it, or it was Luke who said it, but he's already got the box drawn, to which I was like, that was exactly my thought. Once the box is drawn, I think we commit. But is there anybody else who needs to see this one? Nobody at home, nobody in class. Is there another one that you're desperate for in the next 5 minutes? Well, what the hell? Let's go ahead and do this one. So, there's tension acting upwards. There's weight acting downwards. It is accelerating upwards, they said, right? All right. So, I mean, I think the work done by the tension and the work done by gravity are going to be different because it's accelerating. So the work done by gravity is going to be, they tell us how high it goes or something. We do have the distance traveled? All right, so let's just say the whole thing goes some distance h. So we're gonna have mg times h times the cosine of pi. I'm putting pi in there because unfortunately, when I was looking at the stupid stuff for that last problem, in their own notes to the person who's here, they convert their angles to radians before activating the cosine. Because they produce solutions that just look ridiculous, by the way, just so you know. So you really can't figure out what their answer is from their solutions, but they convert every angle into radians internally in the stupid program. So stupid. But I didn't write the textbook. I would love to write a textbook. Someday, you're going to see Physics by Shelton. It'll never sell. Probably because it's got a lot of foul language. So T, yeah, I'd buy that book. T times H times cosine, 0 degrees. This is the total amount of work done. That's going to equal a change in kinetic energy. The problem is we don't know the tension. So that to get the tension, you do have to do net force, which is going to be equal to ma. They do give us the acceleration. So the acceleration is, I forget what it is, but you're going to have T minus mg equals ma. So the tension is going to be mg plus ma. That's probably the part that would throw some folks, that you're going to need to do that for tension. The net work, though, is going to be just the change in kinetic energy of the elevator. So that's how that problem is done. I wanted to make sure I got it all spit out there in the 5 minutes that we had. So that was probably 4 minutes. So I probably have a whole minute left. I am going to post sometime before I go home today a practice FRQ. It is not practice in, let me say it differently. I'm going to post something that looks like your exam looks. Okay. I've given ones that are kind of wackadoo FRQ stuff for you guys to see, but it's time, we're close to the test. So this is going to be a selected FRQ that I chose not to put on your exam, but is more in line with what I would expect you to be able to do on the test. And it might have some adjustments by me because I might have had to remove a piece of it. A lot of them have conservation of momentum in them as well. So I might have had to adjust it, but it represents, just like I told you guys in E&M, it represents more what I feel is a more clear-cut problem that you should expect to be able to do. All right? Any questions about what's happening next 2 days? Tomorrow's our final review, no new material. We're going to talk about the test, do a little practice, go over this FRQ, and then Friday's the test. Multiple choice, 2 FRQs, 7 hours of me watching you guys sweat, and then a wonderful week off. What's that? All right. You guys at home, any questions before we break? All right. We have no idea when the bell rings, but it's got to be soon. Somebody in here says it's like right now, but there's no bell yet.
No, we just stay in this class.
I don't care if you stay in this class.
Okay, yeah.